Please welcome Jay Quan, Tendermint presentation.
Thanks, Larry. And thank you to us Bitcoin devs for hosting this meeting. And hello. Yeah. And thanks to Startup House for hosting it and for ChangeTip for sponsoring. Okay. So before I get started, I want to ask people, how many of you know how Bitcoin's proof of work works? Could you please raise your hand? Okay. It's most of you. How about, have you read any proof of stake proposals? Anybody? Okay. How many of you guys heard of Tendermint? All right. Okay. That gives me some idea. So I have a lot of slides prepared, but I don't want to spend time on everything. So if there's something, I'm going to go fast. If there's something that you guys want to hear about, then raise your hand and let's go into discussion. Let's do that. Okay. Thanks for coming. Tendermint. So I'm going to talk about why Tendermint, why I'm building it, and why I want you guys to know about it. Sorry. And how it works, and then I'll show a little demo, and then I'll talk about where I think where we'd like to get to head. Okay. So why Tendermint? I think of the blockchain as representing a community. It's not just about money, the way I see it. I think it's about people coming together to come to agreement about something. It could be anything. It could be money, but it could be reputation, it could be anything. And if we want the blockchain to represent communities, and there are many, many communities, each with different policies and expectations and experiments that they want to do. Maybe they want to have their own fiscal policy as an experiment. Or maybe they have different expectations about what should happen when money is stolen at a large scale. Maybe they want to experiment with different currency models. Maybe they want to try a monetary experiment where there is no money. I don't know. Then we need many blockchains. Or anyways, that's what I think. I think we need many blockchains. By the way, I'm going to make assertions in this talk, and it doesn't mean that they're true. It just means that I think they're true. So if you think I'm wrong, then please correct me. There have been multiple proposed solutions to create multiple blockchains. In the beginning, there were proof of work altcoins, coins that forked off of Bitcoin. There was proof of stake altcoins, and there's Ethereum with a Turing-complete contract language, very general, very nice. And recently, we're talking about sidechains now. That's what people are trying to innovate upon. I'm going to say that proof of work is going to be, it's necessarily too expensive, or it is insecure. And so that's, it's not proven, but I'm going to try to convince you that that's true. Bitcoin has an energy problem. Well, the price has gone down, so these figures are not entirely correct, but about as of 3 weeks ago, I believe, or 2 weeks ago, the network was spending about $1 million every day in electricity. And that money being spent in electricity and mining doesn't come back into the community. It pretty much leaves. It might come back in somehow, but it's pretty much wealth that is destroyed. The $1 million figure, by the way, does anybody know how I came up with that?
Take the mining reward and then assume the miners are spending roughly that much.
Right, yeah. So you take the mining reward today, which is 25 Bitcoins every 10 minutes, multiplied by the price, and that's going to be pretty much what miners are going to spend in electricity and hardware in order to eke out an ROI. And by the laws of the conservation of Bitcoins, most of that's going to end up going to electricity. And if we assume that Bitcoin is going to win, it's going to dominate. If we assume that Bitcoin is going to dominate the cryptocurrency landscape in 8 years, say, because that's pretty much how technology evolves and comes to dominate, right? Like the internet, first it was Google in 1999, I think, and 8 years later everybody's using it. All right. Then what would happen is the price of Bitcoin would go up maybe 1,000x, maybe 100x. I don't know. The reward would have about twice after 8 years. But if the price of Bitcoin goes up 1,000x, that's $250 million per day being spent by the network just to secure consensus. Just to give you guys a figure, an idea of what that is, I mean, like just $1 million today, that's 5,000 developers you could be paying full time to develop something. That's how much we're just burning in electricity. I'm going to say that you don't need to do that. I'll show you later how. Other solutions that came out, POS stands for proof of stake. But the early proposals like NXT, BitShares, Peercoin, they all had different problems, but the main problem has always been that there's nothing at stake, ironically enough. So what that means is...
What does it mean when we say there's nothing at stake?
Right, okay, yeah, good question, thank you. Proof of stake means instead of having miners compete for creating the next block, you use the blockchain and you use the amount of stake that each person has. So let's say I own 1% of all Bitcoins or 1% of all coins. And that means I have about 1% of power to create the next block. And so that's why it's called stake. It's proof of stake, in that the more stake you have, the more power you have in consensus. The nothing at stake problem comes about when a blockchain is, in Bitcoin, the blockchain is secured by work. So if you want to create an alternative fork of the blockchain, you have to do that much work. But when you have proof of stake, which is based on public key cryptography, where you can sign as many blocks as you want, what's really preventing anyone from creating 1 million forks? There's nothing at stake in the old proposals for proof of stake. Anybody could create as many blockchains as they want. They can fork the blockchain 1 million times, and there would be nothing at stake. They wouldn't have anything to lose. So fixing that is the first thing we have to do. I'm going to skip Ethereum because Ethereum is awesome. But I'll say one thing, that even the way I see it, even if Ethereum takes off and becomes big, there's going to be a need for multiple blockchains just to handle the amount of transactions that are going through. And so the question is, how do you secure all of those many blockchains for Ethereum? What consensus engine should Ethereum use? And I'm going to say maybe something like what I'm going to propose. Let's skip this. All right, so how does it work? Does anybody have any questions so far?
Why are you going so fast?
Because I have like 40 slides and I want to show it to you.
Just quickly, what's wrong with sidechains?
All right, there's nothing wrong with sidechains. I just wanted to say that with sidechains, we heard about sidechains mostly from like Blockstream, when Blockstream is innovating on sidechain technology. And I wanted to say that they're proposing mostly a way to create sidechains that are two-way pegged from Bitcoin. And so that's, as far as I can tell, that's Blockstream's priority. And it's a lot of people's priorities to create a way for blockchains to interoperate, to be able to track transactions that are meant to go from one blockchain to another, but with Bitcoin as the center. And I'm saying that there's no reason why it has to be centered with Bitcoin. We should create a system where you can have pegging sidechains of all sorts, interoperating in different ways, many different ways. And it's not just about two-way pegging. It can be about backing. It can be about bootstrapping a blockchain by backing it with assets on another chain. It doesn't have to be Bitcoin. So that's what I wanted to say. All right, so how does Tendermint work? This part's going to be in two sections, so I'm going to describe the first one, and then I'll ask for questions, and then I'll describe the second. All right, the first part for solving consensus without proof of work is to solve the nothing at stake problem. Right. In order to do that, you lock up the coins so that they are actually at stake. I mean, it sounds silly when I say it like that, but what's happening is before in, say, NXT, when there's a blockchain fork, the attackers, the ones that are forking the blockchain, could have moved the coins while they're attacking it. So in the end, nobody has any idea who attacked it and which coins to destroy. So the way to solve that is to lock up the coins as collateral, so that it's guaranteed that should there ever be a fork in the blockchain, then we know who caused it. And so that is what I call bond deposits. That's what bond deposits are in Tendermint. It's just a way of creating collateral. And so what happens is, in order for me to partake in the consensus process, I have to post my coins in a bond deposit, so it's locked up as collateral. I can't move it after I do that. It stays frozen. If I want to get my coins back, I have to say I want my coins back. It's an unbonded transaction. And afterwards I have to wait a long time, let's say a year. So that means that if I fork the blockchain today, and you tomorrow see this fork and you were fooled by it, this sham fork that I created, this fork of blockchain, you'll know for sure that the ones who double signed, the ones who forked the blockchain, that their stake is still up in stake, that it's still available to be destroyed. I'll get, sorry. So I've never actually had a presentation like this, so if you have any questions, if you don't know what I'm talking about, just raise your hand. All right, so double signing / mistake. I'll get back into this so it makes more sense. Yeah, go ahead.
So the purpose of signing is to sequence the blocks.
The purpose of signings, yeah. So when, right. Everybody who wants to partake in the consensus process pays the bond deposit. Their collateral is frozen, and then they have voting power in proportion to how much they froze. And then people vote. People sign, cryptographically sign the next block using a pub key, public key, right? So, you know, in Bitcoin, when a block is created when a miner mines it into existence, when they find the pre-image collision of a hash. But in Tendermint, that's not how it works. A block is committed into the blockchain, and then a new block is born when it gets signed into existence by the supermajority of validators. And I'll talk about how many need to sign. Well, I'll tell you right now, it's going to be, as long as 2/3 or more of the voting power of validators sign the next block, it is officially committed. Right, so require at least, so when I say plus 2/3, that's just more than 2/3. So require.
Could you step out of the, yeah.
Just want to make sure. All right.
Can you restate that, the difference between Tendermint and Bitcoin blocking and just
The difference between Tendermint and Bitcoin mining. Right. Yeah. Okay. Sure. So in Tendermint, everybody. So in Bitcoin, when I receive a block in Bitcoin, I know that it's the next block because I can tell quickly by looking at the headers that it had the most amount of work done on it.
Can't hear you, sir.
When I see a block in Bitcoin, I know that it is the most recent block and it's the right block because it's included in a blockchain that has the most work done on it. The proof of work allows anybody to look at a bunch of numbers, short amount of numbers, and figure out how much electricity was put into it. So That's how Bitcoin works. You look at this blockchain and you look at how much energy was put into it, and you're like, this has to be the main one because it has the most amount of work. Whereas in Tendermint, it's not about energy expenditure. It's not about creating a collision of hashes. It's about, did the validator set, did the supermajority, meaning 2/3 or more, signed this block? Did they approve of it? Yes.
So how does it keep track of the voting power?
All right. It's deterministic. It's based on the blockchain, and I'll go through it, and then you can ask again if there are any questions. Okay. So why 2/3? When 2/3 or more are required to commit a block, and that means that if there is a fork in the blockchain, it means that at least 1/3 of the validators have had to double sign. And because it's based on public key cryptography, there's evidence of who did that. So it's all rather transparent. Here's a little graph. Nice. So let's say this is the whole pie of the validators' voting power. Let's say that 2/3, more than 2/3, had signed block B, say. And then let's say that another 2/3 had signed block B prime. Well, and B and B prime are at the same height, let's say H. Just by simple arithmetic, you can tell that at least 34%, or at least 1/3, have had to sign, double sign, or sign duplicitously. So signing on both blockchains and causing a fork in order for this to occur.
So that's less than the number of bad miners it takes to fork the Bitcoin chain.
Less than half of Bitcoin? Yes and no. It is true that it's less than half. It's 1/3. There's actually a way to increase this tolerance level. So you could actually go with increase this number, but there's trade-offs. We can talk about it in a bit. Also, Bitcoin has its own, in the face of incentivized participants, it's been shown by Eyal and Searer in a paper called The Majority is Not Enough, that Bitcoin is only robust to 1/3 of the mining power, considering collusion attacks and hiding, not publishing the block. It's a pretty detailed paper. This is pretty technical. All right, so I'm going to skip this. Wait, you guys want to go? Okay. All right. I'll try. So I've been talking about double signing. So what I mean is, I'll just go over it again really quickly. If there's a blockchain, and let's say the blockchain's height is h, right? And we're trying to figure out what the next block is at h+1. The only way the blockchain will fork at h+1 is if 2/3, 1/3 or more double sign, meaning 1/3 or more signed on both B and B prime. That's one way to do it. A better way to do it is actually to do it by wrong signing. What that means is it's not about signing two blocks at the same height, like duplicitously signing that way. It's about signing the wrong blockchain, the wrong block at all. And that way, let's say I'm a validator, and the real blockchain is like, this is the real blockchain over here. I don't know why I'm doing this in my hand, but here it is. 0 all the way to H, all right? Let's say I signed just this random block over here because I just felt like forking it, right? And so here's like B prime or something. It doesn't matter that I didn't sign another block at the same height. As long as I signed the wrong blockchain, that evidence, along with so I'm talking about the signature, the puff key signature, along with that hash, that block hash, can be included back into this chain. And the main chain will then have evidence that I signed at a random block, and I'll get punished for that. The benefit is that you no longer have to store all the signatures for all the blocks. You only have to know the most recent signatures for the validators of each block. So that way you can save a lot on storage of the blockchain. All right, so to sum up, to kind of like think about this intuitively, what are the properties of this? So in Bitcoin is anonymous. You don't know who the miners are. You don't know how much a person has in mining equipment. It's all anonymous because, I don't know, it's just mining power. But with public key cryptography, we have an identity. And by having identity of validators or identity of miners, and by having the associated bonded coins and the voting power known in the blockchain, by having all that be transparent, you can create a system that becomes more secure as bad things happen. Right? So when miners, validators, and Tendermint, when they cause a fork, what happens is their state gets destroyed and they no longer have that power anymore. I'm talking about after regrouping and consensus, and this is a bit more complicated. We'll go into that. What exactly happens when the blockchain forks? It's a bit complicated. It's not automatic like Bitcoin. All right. So it's anti-fragile. And strange thing about that word, because people use it for Bitcoin. I don't really understand how Bitcoin is anti-fragile, but this one seems to be. Am I wrong? All right. All right, so, okay, so, and some people have asked me, when I explain this, some people say, well, so you want to have a lot of blockchains and validators signing. That seems like it's pretty insecure because you're incentivizing validators to not fork the blockchain with the valuable coins that are at stake, but small blockchains have, they're not worth anything, so how does that work? And the answer is, well, I haven't thought this all the way through, but here's a suggestion. You guys run with it. If a validator can actually, because it's a public key, and the public key can be used in many blockchains. If I'm a validator, maybe the promise is that if I wrong sign on any blockchain, you can go ahead and destroy my stake on all the blockchains. So in this way, you can have the security across multiple transcend each blockchain.
If I'm the sort of person who intends to carry out an attack, what incentive do I have to use the same public key on multiple chains?
Right. There isn't. So, but if you do, then you can tell that this small chain, it actually has more security because the validators chose to show the association of their identity. But that's a good point.
I'm looking forward to the mechanism of destroying coins.
Yeah. Something else. How does that process work?
Okay, I don't have any graphs here to show that, but it's pretty simple. When a validator signs, commits a block, what they're doing is they're signing the block hash along with like the network name, like the name of the network, and the height along with the hash. So when I'm the validator, let's say I cause a fork, right? Then, and I do to you with this fork, then you're gonna see that I had signed wrongly, that I had lied, and you'll have the evidence, which is simply the hash and the height and the network name. And you'll have two of these that don't work together. Let's see. That's true with double signing. With wrong signing, it's a little more complicated. You only have one piece of evidence, which is the hash that I signed wrongly on, and you would insert that into the blockchain. And so, with the context of the whole blockchain, you can tell that I had signed wrong.
So there's something on a protocol level where if it senses a wrong sign, then it destroys that bond? Like on the protocol level?
Yeah.
Okay. All right.
Yes.
So if there's multiple blockchains and they're all using like a similar protocol, and I could sign a block on one blockchain, and someone could submit that block as a wrong signing for another blockchain.
Okay, that's why you include the network name in the signature.
So-
So each network, each blockchain should have a unique name, so that it's clear that I didn't, just by signing a block on this blockchain, it won't be confused as wrong signing.
All right.
Yeah.
So in Bitcoin, the miners are at any given time working on many different versions of what may be the next block in the blockchain, right?
Mhm.
So in Tendermint, let's say we have multiple different, I don't know if you call them miners or just signers?
Validators.
Validators, okay. So you have multiple validators. Are they potentially going to produce different blocks, and then one of them might turn out to be wrong, and will they get punished for just being unlucky?
Right, that's a great question, and that is the topic of the second part. And I think we'll get right into it now. All right, yeah? Any more questions? All right, so I've been talking, the part one is all about, once there is a blockchain, incentivizing validators so that it doesn't fork, right? And I'll talk a little more about what that means for the long range, for the long term, because, yeah, I'll get back into it. But let's go to part two, which answers your question of, well, how do the validators come to consensus in the first place, right? Because it doesn't work unless they come to agreement. Deciding on the next block. So in order for the previous part to work, validators have to completely agree on what the next block to sign is. And you solve that using traditional Byzantine agreement research. It's been an active area of research since 1970, I don't know, a long time ago. And people often cite the FLP impossibility result as reason for why, you know, Bitcoin is the only solution or something. I don't know. But so I'm going to talk a little bit about the history of this area of research. So in 1985, Fisher, Lynch, and Patterson came up with this impossibility result. And it says that in a completely asynchronous system, with even one faulty process, it doesn't even have to be Byzantine or malicious, it's just broken. With even one faulty process, it's impossible to deterministically come to consensus, to always come to consensus. And so that was a negative result. But it turns out if you make a small assumption, such as that, the network is not completely asynchronous, it's partially synchronous. And what that means is, say for example, like the internet. Well, we can say the internet is partially synchronous because we know that there's latency. We don't know what the maximum latency is. It's unknown, but it's finite. It's sort of like an assumption. And it's a practical assumption. We can sort of assume that the internet has latency and it'll be fixed if there's any problem. And that's enough to create an environment for consensus. And in 1988, York, Lynch, and Stockmayer published this paper, Consensus in the Presence of Partial Synchrony, that proves that the L in Lynch in this paper is the same thing as the L here. And the FLP, by the way. So, yep. All right, in traditional Byzantine research, there's always a bounds on how many Byzantine nodes we can tolerate. Usually in a partially synchronous network, the amount is 1/3. So if there's more than 1/3 of Byzantine validators, then consensus is not guaranteed. But if there's less than 1/3, then consensus is guaranteed. All right, now I'm going to get into this, the hard part, which is the Tendermint's state machine for consensus. All right. Can you guys sort of at least read the words in the back? Okay, great. So in Tendermint, and this is in all the context of there's a fixed set of validators determined by the blockchain all the way to height h, and we want to figure out what the next block is at height h+1. And all the validators, all the nodes, are going to go through the state machine. The first step is propose, and then it'll go in a circle. So this is the first round. It'll do propose, revoke, and pre-commit, And each of these steps will take a third of the total round time. So if you say that the total round time is a minute, like 60 seconds, then each of these will take 20 seconds. So let's say I'm a node, and I'm starting the consensus process for height h. I'm going to go into propose. I'm going to wait here for about 20 seconds. If I have a validator account and it's my turn to propose, then I will propose and I will broadcast that block to my peers, and my peers will broadcast it to their peers, and so on. And in gossip fashion, hopefully everybody receives it. It's okay if not everybody receives it. So that's the first step. After that, we'll go into pre-vote. By the way, not everybody's synchronized in time. It's okay for all the nodes to be slightly separate, to have drifting clocks. The algorithm counts for it. I'll go for that later. All right, so first step proposed, and then we start voting. The validators, hopefully by the time they each start their own pre-vote step, they have the proposed block from the designated proposer. If they do, then they sign a special vote. It's called a pre-vote vote, and they broadcast it. If they don't, or if they haven't seen anything, they'll sign a very special vote called the nil pre-vote vote, and it's just saying, there was nothing. So I'm just going to say for round 0 of height h, I might nil vote. So that happens for 20 seconds. In the beginning, you do the vote, and then you broadcast it, and then you wait 20 seconds until you hopefully receive all the votes. You don't have to receive all the votes. And then the third step is the pre-commit step. And in that step, if I see 2/3 or more of pre-votes for a block, then I'll say, there's a supermajority that voted for this block. I'm going to lock it up. And I'm going to sign another type of vote called a pre-commit vote and broadcast that. So it's a locking system. First, somebody proposes. Hopefully a supermajority agrees with it. And then everybody sees that everybody agreed with it, and then they lock it up. And then what happens is, for each node, if 2/3 or more pre-commits were found, so if the majority of people locked it up, and you saw that the majority of people locked it up, then you go into the commit stage. Otherwise, you just go back to propose. It's possible that some nodes go to commit while others go to propose. If that happens, they'll eventually converge because, I'll talk about that later. In the commit stage, you wait to receive a block. And we'll get back into that later.
Quick question.
Yeah.
Is it possible that you could have like a capital attack on this where, let's just say, I want to shut your system down, I acquire a bunch of coins, I become a validator, and I just basically throw my votes in to say, no, we're not going to have any transactions going on. Is that
like if I have 1/3 or more of the bonded coins, so if I have 1/3 more of the voting power, and I decide not to sign anything, consensus will halt. Right? And people feel very uncomfortable with this because it's it is unnerving. But I think we should get used to it because of this. When, say, there's a split in the Bitcoin network. So let's say the United States and Europe, for example, the network split. What might happen is one side has, say, 49% of the mining power, while the other side has 51%, right? And it's going to be difficult to determine which side you're on. During that time, it would be best if the entire network could just say the network split, so let's just not commit anything, rather than pretending like everything's fine and continue to mine blocks on each side, when at the end of it, one side, well, the US in this case, is just going to lose. And so it's better to have that in the protocol where it halts, where there is no consensus. That's what I think. It happens to be 1/3 instead of 1/2, but that can be tweaked. All right, so let's skip this. Okay, so this is what I was talking about. when you see 2/3 or more pre-votes, then you pre-commit. When you see 2/3 or more pre-commits, you commit. When you see blah, blah, blah. When you see 2/3 or more commits, then that block is considered to be committed by the network. So there's this difference between a local commit. So I'm a node, and I can sign a commit for a block. That doesn't mean that it was actually committed by the network. It doesn't mean that a merchant should act upon it as if that transaction had committed. The merchant should only act upon it when he learns that 2/3 or more of the entire network, the validator set, can sign it. All right, so in Byzantine consensus, people will talk about safety and liveness. And I'm going to try to very quickly prove safety and liveness to show that this is safe and that it won't deadlock. All right, so safety is when two correct nodes never disagree. Right? So that would be like a fork, saying that this will never fork. Right. Here's why. Do you guys want to hear about the proof?
Yeah.
All right. Okay, great. I don't want to bore you. All right. Good validator. Okay, so let's say that a good validator, so one who's not Byzantine, committed a block. Let's say a block B at some height h. And let's say that this good validator committed, so signed a commit vote for block B. And what that means is, if he signed a commit vote, that means that he saw at least 2/3 or more pre-commits from the network, from all the validators for that block. And if we assume that there's no more than 1/3 of Byzantine validators, then it follows by arithmetic that at least 1/3, more than 1/3 of the pre-commits were by good validators. If that's the case, if 1/3 or more of pre-commits were by good validators, it means that they had locked on B. And the only way they're going to unlock from B is if they see 2/3 or more signed for another block. But that's not going to happen because 1/3 or more are locked on B. They're never going to see 2/3 or more vote for something else. So they're going to remain locked on B, and if they progress at all, they will progress towards B. That's the proof. It's not robust, but I'm not very good at writing, robust proofs. I'm not an academic, so somebody else could help me out here eventually. But I believe it's correct because it's based on the paper, and the paper is correct. Liveness. So this is saying that the network won't deadlock. Blocks are eventually committed, and this is more detailed. I can't really go into right now. I could try. There's a proof of block thing. So what that means is when I'm a node and I lock on a particular block, I also remember the list of pre-votes that caused me to lock it. And when it becomes my turn later to propose a block, I have to propose the one that I'm locked on, and I'll also disseminate the list of pre-votes that caused me to lock. And that will cause anybody who's still locked on something else from prior, to unlock, because they'll see that actually the network had progressed onwards. Sorry, I don't have much more slides for this, but that's a shame. So these boxes were shaded, but they don't have to be shaded here. Okay, so now I want to talk a little bit about partial synchrony and how it works with partial synchrony and drifting clocks. Okay, so I've sort of assumed that all the nodes have a somewhat accurate time, that they're somewhat converged. Because if nodes are at completely different times, then they will be at completely different rounds, and this thing would never work. And the way to solve that, at least in the DLS paper, is to have subsequent rounds be longer than the previous one by a fixed amount of time. So round 0, or round 1, let's say 1 here. This is the first round. Let's say it takes a minute, and this is one node. This is another node, and this is another node. So these are 3 nodes, and this is time. This is the time axis. So at this time, this node 2 is on round 1. He's the only one on round 1 for this height. And then eventually he'll go into round 2, which is longer than the previous round by a fixed amount of time. In this case, twice as long. Right? And then it goes into round 3 and round 4, all of which are longer than the previous by another whole block. And I just put this in here to show you that even though they start off at different times, and so even though the first round of that height are completely mismatched, and so they're not on the same round, eventually they will be. So here you see that round 5 is overlapping for all 3 nodes, and they're able to converge upon the same round. Right.
Does this time convergence is categorically going to happen, or if the network somehow senses that there's asynchronicity going on?
It's always happening. So if for any reason a node cannot find that block is committed for round 1, for round 2 it will always be a little longer than the previous one. And everybody does it subjectively.
Does this extension ever reset, or is it just constantly?
Right. Okay. It resets. Yeah, I forgot to include that, so thanks for asking. It resets the beginning of the start time for the height. Resets when a node when it first sees 2/3 or more of commits.
I can't hear you. What did you say?
The beginning of the consensus mechanism for the height for all nodes, for each node, resets every time it sees 2/3 or more of commit votes for the previous block. So on the gossip network, when I see 2/3 or more of commits, because I'm tallying these votes as I see them, when I see that it had reached its threshold, that's when I reset the clock. And so in that sense, everybody's clocks are synchronized by the network. So if the network is fast and efficient, the clocks are going to be more synchronized. If the network isn't, if it's not doing so well, then.
Did you say that it was when you see 2/3 votes for the previous block though, that it resets?
Yeah, because all votes are always for the previous block. Yeah. Yeah.
Each new good block, you start to convert.
Yeah, each new block, the time resets.
It has to be a good one, right?
It has to be a good one. Yeah.
So how long it takes to commit was based off overall network latency or just overall network?
What was the question?
So how long it takes to commit a new block will depend on how synchronous the network is overall?
Mm-hmm. Yeah. If the network, let's say that the network latency increased to, let's say, 30 seconds to a latency between the US and Japan or something. I should show it here.
This is just the latency though of validators, right?
The validators are running on the nodes, so yeah. Well, okay, so actually all of this I've been talking about just runs on nodes, whether or not you're a validator. If you happen to be a validator, then you also do the signing and the proposing. But each node has its own round state. It does the timing thing. It goes stepwise.
I'm just thinking of like incentives if you wanted to attack and you were always claiming that you have really high latency, then you could disrupt a little bit. But if you're a validator and you have stake in that, then probably game theory.
Yeah. If you're a validator and you're just not signing things on time, then it's not in the slides, but it's in. I don't know if it's in the paper or not. But after about, say, 10, 20 blocks of not participating, not committing, you are automatically timed out. So it's deterministic because it's based on the blockchain, right? If you look at the blockchain and the signatures and you see that this validator who was supposed to be signing hadn't signed in the last 10 blocks, he becomes unbonded.
But if that's over the 1/3 of the stake, the network halts instead.
Right, but if 1/3's doing that, it just halts.
Right. So any users less than 1/3 of the capital, if they're not getting connection list timeout, but anything more, it'll halt the network.
Yes.
So the commit time is going to sort of be like a representation of the global internet efficiency almost.
Yes.
So the faster internet got, the faster commit time we get.
Yes. Yes.
So I have I think for small blockchains, it's likely that this whole thing could finish potentially even faster than 1 minute. So one way I think you could actually even improve this is if you start off the commit time at 1 second instead of 1 minute, and then increase it exponentially, but multiples of 2 instead of increasing it by 1. Then what you would have is like you would, if the internet is really fast, then it would get done in like 4 seconds, 8 or 16 or whatever. But then it would still pretty rapidly reach whatever time it has to be, even if it's longer.
Yeah, that's great. I completely agree. I have been thinking about ways to improve the time convergence of this thing by making it exponential. And even perhaps by varying the initial round time based on the past performance. So that might be another way to do it. So it can actually theoretically be tuned, it can tune itself to be
It's like a
very
difficulty
efficient.
curve.
It's like the difficulty, right?
Change over time, right?
Yeah.
Based on previous performance.
Sorry.
Yes.
Is this something that you would build into your own coin, or is it something you would develop into a pull request for other coins?
This is I can show you this later, but this is all inside the consensus submodule in the Tendermint project. And if all coins, if they wanted to tweak something, they probably don't want to tweak this. Maybe they do. I don't know. They would mostly be editing some other submodule. It would be an independent part of the project. Okay. So a little note on proof of work and forking, because people, even myself when I started this, had the notion that if we want to create a proof of stake algorithm, we have to figure out which blockchain is the best one, by, I don't know, figuring out the total difficulty of it, the total amount of energy or stake that was put into it. And I don't think this is the right way to do it for proof of stake, because, well, the reason why you need to do it for proof of work is because miners are anonymous. So the only way to tell how much power they have is to, over time, figure out how many blocks they mine. It has to be a forkful system. But in proof of stake, I don't think that's the case at all. So, and that's because proof of stake is more based on identity. How much time do I have? How long is it?
10 minutes.
Oh God. All right. So. All right. So. Any questions?
Okay, so as a validator, 2 questions. The first was, how do I know if I want to sign a block or not? Is that chain-dependent set of rules? Like every chain has its own set of rules on whether a block.
Oh, I see. Yeah.
So
like the order of proposers, right?
Right.
Right. I have one created for Tendermint. I don't really see why you would want to change it. It does this thing where you add your voting power to a variable that gets stored, and it gets accumulated. And then every round or every height, you add to your accumulation value your voting power. And the proposer is the one who has the most of the accumulated points.
Okay, so that's your round robin. And I'm sorry, the question was, if I see a block as a peer, how do I know it's valid? Right? Is it just every chain has its own set of rules that I'm validating? Right? Like Bitcoin, the ins and outs need to be balanced, right? So,
yeah. First, you would receive the commit votes for the block.
okay.
You would receive 2/3 or more that vote for the same hash, and then you would know which block to receive.
Okay, so I guess the question is a step lower than that, is to put my signature on it. I don't want to sign invalid blocks because I'm going to lose my stake.
Right.
So the decision as to whether a block is invalid is part of the particular chain's protocol. So a given chain, let's say a financial chain like Bitcoin, but how to say the ins and outs need to be balanced.
Right, yeah.
Is the rule that makes the block valid.
Yeah, going back to, say, the state machine, if the block were invalid, hopefully everybody agrees on whether a block is valid or not. They would pre-vote nil if the proposed block is invalid.
Got it. Okay, and then the follow-up question is, provided I have some stake in the chain and I want to do voting, where do those initial coins come from? What's the bootstrap procedure? for validating?
That's a great question, and I'll get back into that. I think there's a lot of solutions here. There's so many solutions that I just like, yeah, I can't decide on one, but I think I have conversed upon what I want to do for Tendermint. But like in the very base case, you could have exchanges solid, or you could have as an IPO, right? Or you could integrate proof of work into it that phases out over time. But I'm sure there are better solutions.
Fundamentally, Bitcoins come out of the Coinbase for a given block. Where do the coins come from in Tendermint?
Okay, you can do anything. You could start from a single address that has all the coins and give them away, or you could do something.
So like the validation rule is specific to the blockchain, right? You have a chain with set
Yes.
rules. Coin origin is part of the validation rule.
Yes, and I hope everybody forks Tendermint and creates their own. Yes.
So there's a security implication to coin issuance too, because if I'm looking at the internet, I come along the Tendermint blockchain. Like, if I don't know how the coins were issued initially, I don't know what is the security of the distribution of the validators. And so that's like, it is an element of like an extra protocol piece of information that you need to know when you're deciding on the security of not just how many coins are bonded, but if those coins were, there could be 100 private keys, but they could be owned by the same 2 people. It does create the risk of somebody creating a false reality for who wants to double spend again.
Yeah. So before you use or accept a coin, it would be best if you could look at the validator set and be like, yeah, I trust these guys, I trust this network. I don't know, or you're crazy and you just want to receive coins.
Yeah, I mean, it seems like your talk is strictly just focused on consensus, just consensus. Is that
So far, yeah. I'll talk a little bit about what I want to do with my coin. I don't even want to call it my coin because you'll see why. Alright. I'm gonna skip this stuff like it's a hot potato. Gossip. It's based on a gossip network, so it doesn't assume point-to-point connectivity. I think that's great because it's more resilient. Nation states can't shut it down based on IP. U2XO versus accounting. So Bitcoin uses the unspent transaction output as a way to keep account of coins, whereas Tendermint uses the accounting model. So there's an account and you can add coins to it. It's not about individual unspent transactions. There's been some people who told me that the accounting model is not good because it's less private and also because it's unprunable. And I think for the first one, whether it's less private or not, it really depends on the client implementation and whether it's unprunable. There's a workaround that I won't get into. You can ask me about it. It uses a self-balancing, Merkleized, immutable tree to keep track of the state, much like Ethereum's Patricia tree. It happens to be an AVL balanced tree. So the AVL tree is like the first balanced tree algorithm that ever came out way back in 1980. Everything I build is based off of 1980s technology. It's awesome.
Everything all of us build is based on.
All right. And also for the propagation of blocks. So like going back to the state machine, there's a lot of blocks being proposed. The proposed block needs to be able to transmit across the network very quickly. And the way I solve that in Tendermint is with a Merkleized set of the parts of the whole block. So you split the block into multiple parts. These should be hashes, by the way. So this should represent the hash of the first part of the block. So if this is like a 1 megabyte file or something, these are 6 parts. This is the hash for the first part, the hash for the second part. So what this does is when I receive, let's say I have a node and I receive a part, as soon as I receive the part, if I receive also the hash for the uncle here and also the uncle here, then I can reconstruct the root hash and make sure that it matches with the one that the entire validator set signed. And so because you can quickly verify the integrity of the block, you can broadcast it immediately to your peers, and that allows for faster transmission across the gossip network.
We got 5 minutes.
All right. Yeah. All Alright, I mean, there's like, I use, Tendermint uses ed 25519. It's very fast, 70,000 transactions per second. It's pretty cool. Not transactions, but signature verifications, sorry. I have an open question, maybe somebody can answer, which is there a way to do cryptographic threshold signatures using ed 25519? And is there a library for it? I know Ripple wants to do it, but I haven't seen it.
You should ask Stefan Thomas.
Okay.
Stefan at ripple.com.
Okay.
He's implemented it.
All right. You guys want to see a demo?
Yes.
Okay.
Quick.
Let's see if it still works.
At least 2/3 of us must have.
All right. So this is not okay. This is a separate project on the GitHub repo, Tendermint front end. I just built it in the past 3 days or so. You can see the blockchain. Let's see, it's running on my laptop. I have a validator that's running. It's connected to a Linode instance, so it's actually just a node of 3 machines, a network of 3 nodes. But this is the most recent height at 995, producing one every minute. And you can see that, okay, so I'll click on this. So this is the block down here. You can see that it has a header, it has transaction data, and it has validation. Let's look at the header. So this is the height, time. It has a state hash, so it keeps track of the state of the IAVL tree that I was talking about. So that, and because the state hash is included in the entire block hash, you can actually query any part of the state. So, for example, this means a thin client of the phone can ask what is the most current account balance for this account, and it'll be able to tell you, and you'll be able to know. The validation is the commit signatures. Let's see. Anyways, you guys should check this out. I was gonna do a demo of signing transactions, but
how big is the block? How big is the block?
Well, there's no limit on it right now, and there's no transactions on it, so it's very small right now. But hopefully it'll grow to be much bigger.
What does an address look like?
What does an address look like?
Yeah.
Right now, it's just a hex. It's just a hex value. So let's see.
25519.
Yeah. So I just generated a priv account, and priv stands for private. So this is private data that I just generated. You could use this to, this will be your wallet, right? This is your address, and I forget how many bytes that is, but that's ed 25519 public key. Hashed, by the way, hashed using RIPE 160. So that is your address, which is the hash of your public key down here.
Does it always start with the same digit?
No, no, I don't.
A and a B just looks similar.
Yeah. No, I don't have any of those like base 58 things. I mean, maybe that'll be added later. Yeah.
How many of you are working on this project?
I started in May.
How many of you work on this project?
Oh, me. Actually, Zaki recently made a commit. All right, really quickly. All right, where I want to
Got 1 minute.
All right, 1 minute. All right, man. So where to? I'm just gonna talk. I don't want to have this thing where I have all the coins and I distribute it. I think it'll be way more fun if I don't control the network, rather if I am just another member. And if we create on the blockchain a system of governance so that we can all decide who to give coins to. And so there's no cap, there's no rules. We just kind of set the rules and make the rules as we go along. So if you guys want to participate in the experiment, then email me and we'll get going.
Why don't you give it to Stellar? They have a consensus problem.
They haven't asked me, but you know they're all free to use it. So yeah. All right, thank you.